Okay, AP Chem class, this second part of the video is going to cover the subject of double replacement reactions and net ionic equations, which is the main theme of the Day 35 assignment. Let's go ahead and talk about that. It might take a little bit of practice to get good at this. It does in a lot of things in chemistry, so don't get discouraged. Just keep practicing, come in and work with me, watch the videos, and this will come through. It's not impossible to understand. So, a double replacement reaction, we talked about those in the first video. It occurs between two ionic compounds. So this is a very important type of reaction, the double replacement and the net ionic equations, because there's really two important types of chemical bonds that we talk about in this class, ionic and covalent. Metallic bonds are a third class, but we don't talk about those that much. So this is talking about how do ionic compounds create chemical reactions. So it's an important concept to understand. So double replacement reactions occur between two ionic compounds. A net ionic equation shows only the elements and compounds that take part in the chemical reaction. It does not show elements or compounds that dissolve in solution and remain dissolved. And this is why oftentimes chemists want to use them, because the things that are not important, it gets rid of. Think about if you're making something with onions and you want to have a recipe that calls for onions. And you talk about how you peel the onion and then you chop the onion up in a certain way. Well, you don't talk about in your recipe, what do you do with the scraps that you peeled off the onion? You kind of throw them away. And it's the same thing here. If there's elements or ions rather in a solution that don't really take part in the reaction, you don't want to show those in a net ionic equation, because they really don't do anything. They're just kind of cluttering up the equation. And so chemists often write, in terms of ionic compounds, often write net ionic equations. So the process of writing a net ionic reaction involves three steps. One, you write a complete molecular equation. This is the complete double replacement reaction that you saw in the first video. In other words, it's a chemical equation in the form of what you're used to seeing a chemical equation look like. Complete ionic equation. The next step is the complete ionic equation. This is where you break each of the ionic compounds into their separate ions. And this equation is going to be pretty long. It's got a lot of pieces to it. And so you want to give a lot of space across the page to write this. Finally, the net ionic equation eliminates the ions that do not take part in the reaction. So to write these, this is where we get into these phases of matter that you've seen sometimes, these letters that are behind chemical compounds. Many of you asked what they're for. So a chemical reaction can produce four phases of matter that are important in double replacement reactions. The liquid phase, and that's abbreviated by the L. So this is an L, not a 1, and it stands for liquid. A liquid is a pure substance such as water. It is not a solution. The solid phase. A solid is a compound that does not dissolve in water. It produces a precipitate, and that's a solid that usually sinks to the bottom, or it's definitely distinct from the rest of the solution. Maybe it has a different color to it. Gas. A gas is an unconnected molecule or unconnected molecules that can exist in air or in solution. For example, the carbon dioxide in a Coke is a gas. It's a gas that's pressurized and put into the Coke to carbonate it. And finally, aqueous solution. This is very important. An aqueous solution is a mixture of a solute in water called a solution. A solution is not a liquid. Generally, when a ionic compound will dissolve, it forms an aqueous solution. Okay, so now we're going to get into an example, and it will make a lot of this a lot clearer. To do this example, you're going to need three things. You're going to need your periodic table of charges. And that is this sheet that you have. Yours is blue. I'm using a white one here. You're going to need your 60 common ions. That's the orange sheet that you've been using on quizzes. This sheet right here. And finally, you're going to need your solubility rules. For today's assignment, you won't need the nomenclature sheet, but I will get into some problems later on where that is going to be useful. Okay, so here we go. we are going to go ahead and write a net ionic equation for a chemical reaction. So it's very simple question. Write the net ionic equation for the following reactants: barium chloride and magnesium sulfate. So the first thing you do is you switch the cations with the anions, and this is the complete molecular equation. So you take this and you take the barium and you switch it over so that it's with the sulfate. There it is right there. And then you take the magnesium and you switch it over so it's with the chloride, and there that is right there. And that's the double replacement reaction. Okay, the next step is step number 2, is to determine if each of the compounds is soluble, and you get the solubility rule sheet for that. So let's take each one separately. The first compound in the reactant side is barium chloride. That's BaCl2. So you come up here and you see that chloride is soluble except with 3 elements or 3 different ions, and barium is not one of them. So barium chloride is soluble. Magnesium sulfate. Come over here. Sulfate is soluble down here, except with these 5 ions, but magnesium is not one of those that makes an exception, so magnesium sulfate is soluble. Now we go over to the product side, and we have barium sulfate. So we come over here, and sulfate is soluble except with these 5 ions. Barium is one of those, so that means that compound is insoluble. It will come together in water and it will stay together, and that makes it a precipitate. Finally, magnesium chloride is the last one. Again, we have chloride here. Magnesium is not one of the exceptions, so therefore magnesium chloride is soluble and will not form a new compound. Okay, the soluble compounds dissolve, that is, come apart in water. Since barium sulfate does not dissolve in water, it becomes a solid called a precipitate. Precipitates are solid S compounds that sink in water. They either sink or they're distinctive, as we talked about earlier. It may form a different color. If the color does not spread throughout the solution, it just it's kind of sitting there by itself, and you can definitely tell where it is. The rest of the ions do not recombine with other ions. Now we can write a complete ionic equation. They form ions in aqueous solution. You can add these phase abbreviations to the complete molecular equation. So basically, there's still our complete molecular equation, but the compounds that will not come together, that stay dissolved in water, in other words, this is soluble, 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 you put AQ after it, they're aqueous. Whereas the compound that does form a solid, you put a solid after that. So this is your precipitate. Okay, the next step is, once you have this, you balance the complete molecular equation. So it's already balanced. If you check this out, everything balances out. So we're in luck there. You don't need to do anything further for that. Next is step 4. And step 4 is you write the complete ionic equation. That's the second of the 3 equations that you're going to write, and it's the longest one. So you got plenty of space across your page for this. So what you do is you break each of the soluble compounds into its ions. You don't break the insoluble compound, in this case barium sulfate, into an ion. So what we do is we can look at our periodic table of charges. And we see when we take barium chloride here and we break it, we end up with barium is a 2+, right there, 2+, and chlorine is a 1-. So it takes 2 chlorines to take in the 2 ions that barium throws over to it. So barium throws 2 electrons off, chlorine, 2 different chlorines each catch 1. Be careful here. This is not a chlorine molecule. It's not a Cl2. It's in solution. It's not a gas. It's not one of the diatomic gas molecules. So you got to be careful. What it's forming is 2 chlorine ions, 2 different chlorine ions that are separate from each other. They're not together. Once this compound breaks up, you have a barium ion, you have a chloride ion, and you have a second chloride ion, and they're all separate from each other. We'll talk about this concept of spectator ion in just a moment. Now, the magnesium sulfate up here, same thing. The magnesium breaks off and it is soluble. So there's magnesium, it's 2+. And you have the sulfate. Now, you can't get that off of the sheet that I'm just showing you, so you have to come to your 60 ion sheet, and there's sulfate. It's SO4 2-. So there it appears right there. Now we go over to the product side, and we've already stated that barium sulfate is insoluble in water, so it's actually going to come together to form a solid. You don't have any charges, because if it comes together in a way that the negatives and the positives balance each other out. Next, the last one is magnesium chloride. We said that's soluble. So this is a compound, although it looks like it's a compound that's going to form from this reaction, it never forms. The magnesium is still a 2+, as we said earlier, and the chlorines are 1-, so you need 2 of them. So they stay in ion form. They never come together in a solution. Okay, so both the reactant compounds are soluble, so they break into 4 ions. If either of these 2 reactants are not soluble, then this reaction can't take place. You have to have both of them break up in order for them to trade cations and anions with each other. So both are soluble, and they break into 4 ions. Notice that the Cl2 in BaCl breaks into 2 chlorine ions. It's not a chlorine molecule. It's not a Cl2. It's 2 Cl ions. On the product side, the BaSO4 forms an insoluble solid compound called a precipitate, which sinks in water. This is indicated by the S for solid. The magnesium and the chloride do not form a compound because of the solubility rules. In other words, they're soluble in water, so they're not going to come together. The aqueous state is used when ions are separated in water. So in boldface, I put down here, when AQ appears behind an ionic compound, it means that the compound does not bond in water. It forms separate ions. Okay, so let's talk about the concept of spectator ions. We see that the Mg2+ and the 2Cl become ions on the reactant side, and they remain as ions on the product side. In other words, they don't change. Since they play no part in the reaction, they are called spectator ions. Like spectators at a basketball game, they play no role in the reaction. They're just there watching. So let's go back to this page here. And we see that we have a 2Cl here on this side and a 2Cl here on this side. It didn't recombine with anything. So what you just generally do is lightly cross it out. And we have magnesium here and magnesium here, magnesium ion. So they don't play any role. You cross them out. The only ones you keep in the net ionic equation, that's the final equation we're writing, are the things that change. So over here you have a barium ion, but it combines with the sulfate to form barium sulfate. So I've circled the ones that are going to be part of the net ionic equation. So we'll go back to the next page. And that's how you finish out this problem. You write a net ionic equation. A net ionic equation excludes the spectator ions. These are circled in ions in step 4, the previous step. So there's your final product of this. There's the net ionic equation. The barium ion plus the sulfate ion combine to form barium sulfate. And that's all there is to this. It'll take a little practice. It's 5 steps. I'm going to give you 3 of these to do today, and we'll continue to practice these in the future. So let's go ahead and do the rest of the assignment. And we'll go ahead. I would ask that you do these on line paper. They take a little bit of space, and rather than just leaving acres of blank space on white paper here, why don't you just grab some line paper and do these. The rest of the problems down below, you'll see there are some more problems, including a limiting reactant problem, because we need to practice those. You can do those on this sheet, but go ahead and do the net ionic equation problems on a separate piece of paper. Okay, so here we go. I'm going to do problem 2A on a piece of lined paper right there. Be sure to write your name on it and staple it to this. So we start off with barium chloride again. and we add to that, and that's an aqueous solution. So that tells us it's soluble, but we're still going to check our solubility rules. We may not know that before we get started. And we're going to add to that magnesium sulfate. This is the problem that we just did. So I want to see you do it without looking at the example up above. I'm just doing the same problem again. So what do we do first of all? First of all, we switch the cations with each other, so we end up with barium sulfate. And let's pretend like we don't know whether that's soluble or not. And then we have magnesium chloride. All right, so we go to our solubility rules. That's the next step. Okay. And we see that BaCl2, barium, Cl is soluble except with these three, but barium is not one of them, so it is aqueous. Sulfate we see is soluble except with these 5 ions, but magnesium is not one of these 5, so it is soluble. It's also aqueous. Over on the product side, we have barium sulfate, so we come over here. We have sulfate, which is soluble, but barium is one of the 5 exceptions, so that means this compound is insoluble. So we put a solid after that. And finally, we have magnesium chloride. So we have chloride here. Magnesium is not one of the exceptions, so it is soluble, so that's aqueous as well. So that means this is a compound that's never going to form. It'll just simply stay as ions in solution, even though we're writing it as though it is going to form. This is the complete molecular equation. All right. Okay, next step. What do we do? Well, we balance it. Once we've got the complete molecular equation, we balance it. We saw in the example that it's already balanced. You can see that there. You can count the atoms on each side. So we're good to go with that. All right. So next up, what do we want to do? We want to write the complete ionic equation. That's the second of the 3 equations. Okay, and this one's going to be long, so I'm literally going to start way over here on this side of the paper. All right, and so what I have is Ba, and it's a 2+. I know that by looking at my charge number right here. Ba is a 2+, and that's aqueous. It came apart in water, it's still aqueous. Okay, then we have plus chlorine. Now the Cl2, again, this is 2 different chlorine ions. It's not a molecule of Cl2. So it's 2, you use the coefficient 2 and then Cl minus. You have 2 separate Cl ions, and they are also aqueous. Now we have magnesium. Magnesium is a 2+, and that's aqueous. And sulfate is a 2-, and that's aqueous. So everything on the reactant side, dissolved. It's all a bunch of ions. Okay, now we come over to the product side, and the Ba came over and joined up with the sulfate. We write that as a compound because we look at our solubility rules again, and we see that sulfate is soluble in water except with 5 exceptions, and barium is one of those. So this is going to form a solid, and in most cases it'll sink to the bottom. Okay, and then we have magnesium. That's aqueous, and 2 Cl minus ions, and that's also aqueous. And we know that because we see that chlorine is soluble. Chlorine is soluble except with these three, but magnesium's not one of those, so it is soluble. Okay, so this is our complete ionic equation. Now what we do very simply is we go through and we just lightly cross out the spectator ions, okay? So you have 2 Cl on this side and 2 Cl on this side. They didn't recombine, the Cl didn't recombine, so it's just floating around watching the rest of the reaction take place. We have magnesium here, we have magnesium here. It didn't recombine with anything, so it is just floating around watching the reaction. It's a spectator. So what we have left is the barium and the sulfate, which do join together to form the barium sulfate. So our final answer, our net ionic equation, is Ba2 plus aqueous plus the sulfate, 2 minus, and that's aqueous. But when they come together, they form a precipitate of barium sulfate. And that's a solid. And that's it. That's action, and that's lead nitrate and sodium sulfide. So the first thing we want to do is see if they're soluble. Now I already wrote the letters AQ, so that kind of answers that question, but what if you didn't know that? So you go to your solubility rules, and here you look that nitrate is soluble. Anything in this top row is pretty much soluble with anything. So this is soluble. That means it's going to dissolve, so we're going to put an AQ after it. It's going to become ions in aqueous solution. And sodium, similarly, you have sulfide over here, but the exceptions for all anions is sodium. So sodium is an exception. So this overrules this. So it is soluble. If it's got sodium, it's soluble. So this is also an aqueous solution. Okay, so that's the first step. Determine whether you even have a reaction, because if either of these are not soluble, you've got no reaction to take place. So now what we're going to do is we're going to swap the cations and the anions. So the Pb is going to take the place of the Na, and the Na is going to take the, they're going to swap places. Okay, so the Pb, what is it? Well, the Pb is going to be a 2+. Could it be a 4+? No, because nitrate is a 1-, and you're multiplying that by 2 because you have 2 of them there. So it's Pb2. So those are in balance. So we know we have Pb2. Now we come over here, we have sodium, and that's 2 times 1+. Sodiums are 1+, and if you're not sure why, come over here to your charge sheet, and it's a 1+. It's in the first column. And sulfur, this is sulfide right here, is a 2-. So each of the sodiums is going to throw off an electron, and sulfide likes to take in 2 electrons, so it's a 2- that we see right here. Therefore, you need 2 sodiums, each throwing off 1 electron to give the sulfide its electrons to catch. So everything's in balance there. So now what we're going to do is swap everything around. And we are going to get Pb S. So there's your cation, your metal, and there's your anion, your nonmetal, plus Na, and it's NO3. Okay, let's see if our charge is balanced. So we had a Pb with a 2+ here and a sulfide with a 2-. So these two are 1-to-1. It's 2+ and 2-. That works out just right. You don't need to add any subscripts. What if they weren't in balance? That's when you would put subscripts down here, okay, to get the charges to balance. So we're going to be sure the charge is balanced first. Next is sodium, which is a 1+. It's in the first column. And nitrate, which we've already said is a 1 minus. It's a 1 minus right there. We needed 2 of them before, but now we only need 1 to balance with the sodium. So that's 1 minus. So those 2 are in balance. I really didn't have to put it in parentheses, but I wasn't sure until I balanced the charges. So that is your double replacement reaction right there, and that is your complete molecular equation. Okay, so there we go. Now we're ready to move on. We've determined that the charges are set up properly. Okay, now we want to check the solubility of these 2 compounds over here. So we get our solubility rules for lead sulfide, and we see that sulfide is insoluble except for these 3 elements, but lead is not one of these 3. So this makes it an insoluble compound. So that means the lead sulfide is going to be a solid. And sodium nitrate, well, both sodium and nitrate are always soluble. You see them up here on the top row, both of them, sodium nitrate. So that's soluble, so that's going to stay aqueous. So those are never really going to form, they're not at all going to form together as a compound, these 2. But these 2 will. So you have an aqueous, a solid, and an aqueous. Now that you've done that, you have to balance the reaction. We didn't have to do that with the first one. It was already in balance, but this one's going to require that we balance. So what I'm going to do is write it a second time, just a little cleaner. For the purposes of balancing, I'm not going to put all of the aqueous and solid and so forth. It just kind of clutters it, trying to get the thing balanced. So let's do that. You feel like you can work with that up there, fine. I'd prefer to just make it a little cleaner so you can see it better. Okay, I'll teach you a little trick. Whenever you have one of these covalently bonded ions like nitrate or sulfate or phosphate, you can almost treat it like an individual element. So when I come over here to balance and I'm going to write Na is one of my elements, Pb is one of my elements, sulfur is one of my elements, and I'm going to go ahead and just put down NO3 as one of my elements because it's not going to come apart. This is not going to break apart into nitrogens and oxygens, okay? So let me get back on the screen here. So let's count. I have 1 Pb on this side. I have 1 Pb on that side. Sodium, I have 2 on this side, and I have 1 on this side. Sulfur, I have 1 on this side and 1 on this side. And the nitrates, I have 2 on this side, 2 of this entire parenthesis compound here, and 1 on this side. Now, if you're not comfortable doing that yet, you don't feel you're proficient enough, you can always, A, you can use the box method, or B, you can just break it into 2 nitrogens and 6 oxygens, and, it's going to take a little time to do that, but you can go ahead and do that. Okay, so what are we going to balance? We can't balance lead or sulfur because they're already in balance. Let's balance sodium first. So I'm going to put a 2 on this side, so that makes this a 2. And it also makes my nitrate a 2, which I want. So it makes that a 2. So ta-da, all I had to do was, one simple number there, and you ended up with a balanced equation. So I'm going to come back up here, and I'm going to put the 2 here. Okay, so now we have a balanced complete molecular equation. All right, now we're ready to start breaking this thing into ions. And that's going to be our complete ionic equation. Get myself back up on the screen here. Okay, so here we go. So what do we have up here? We have a Pb with a 2+. So we're going to start off, and I'm going to start way over here because, again, this is going to be a long equation. I'll try to write small enough that it appears. And that's a 2+. And that's aqueous. It dissolved. It broke up. Now, what do we have here? We have two nitrates. They don't stick together like a molecule. They break up too. So your lead breaks off, a nitrate breaks off, a second nitrate, because you have two of them, breaks off. They're three separate ions in solution, in other words. So that means you write it as plus 2 NO3, and each one is a 1 minus. And usually you don't write the 1, you just write the minus sign. And that's also aqueous, it dissolved. What do we have next? Here we're going to break up, and each of these is going to break up into a separate ion. So again, you're going to have three different ions. You're going to have a sodium, you're going to have a second sodium, and then you're going to have the sulfide. So it's going to be 2 Na plus, again, this is not a molecule, this is two separate ions. They're different. They're not together just because you write them like this. They're separate. They're floating in different parts of the solution, in other words. And then you add to that a sulfide, which is a 2 minus. Okay. And now that's going to come over to the product side. And we have our precipitate here, PbS. It's balanced. It wouldn't stick together if the charges weren't balanced. It's a 2 plus up here and a 2 minus, the balanced charges, and that's a solid. You think if it's lead, it's going to sink to the bottom probably, okay? And then, now we balanced this one over here and we added a 2 there. So that means we're going to end up with 2 Na plus ions. And over here, we're going to end up with, remember the 2 on a coefficient applies to everything in that compound. So we're going to have 2 NO3 ions. And that's a minus, that's a 1 minus. Okay. And I should have written that these two are aqueous. They don't come together. This never forms a compound. And this is aqueous. It stays dissolved in the water as ions. Okay, so now what you do is you're going to write your net ionic equation simply by canceling out the spectators. Okay, so here you got Pb2 plus. Over on the product side, does it appear anywhere? No, it appears in the compound. So it's not a spectator. It actually takes place in this reaction. Next, you have 2 NO3, and over here you have 2 NO3. So the NO3 doesn't do anything in this reaction, so you cancel it out. It's a spectator. I'll just write that word the first, a couple times I do this. Spectator. And this is a spectator. It's just watching the reaction. Finally, we come to 2Na. It appears there, and it appears there. I should have written aqueous here and aqueous here. No, not aqueous there. Sorry about that. Aqueous there. So 2Na aqueous, 2Na aqueous, that's a spectator. So this is also a spectator, these two. Finally, I have the S. That's an S2 minus, so a little hard to read. But that combines with the Pb to form the lead sulfide. So that means I'm going to circle the ones that are actually part of the reaction. In other words, they don't appear exactly the same on both sides. Okay, the lead combines with the sulfide. It doesn't appear just as lead ion. The sulfide, same thing. So this, and this. So your net ionic reaction is Pb, 2 plus, aqueous, plus S, 2 minus, and that's aqueous. And then finally they combine to form a solid precipitate, PbS, and that's a solid. So you put an S there, and that's your precipitate. Okay, and that's that. That's how you do that. Okay, here's our third problem. It's iron nitrate, and that is being joined with potassium hydroxide. So what I want to do is I want to figure out what the charges are on each of these ions, because I have to be able to write them individually with their charge. So iron, let's look at iron. it can either be a 2 plus or a 3 plus. So which is it? You don't know. Well, here's how you tell. It's paired with nitrate. Nitrate, if we look over here, NO3 minus is only a 1 minus. It doesn't have any alternate charge. And since there's 2 nitrates, that means it's 2 times 1 minus. And when we're talking about charges, we always put the number first and the minus sign or the plus sign after. It's a little thing, but that's the way it's done. So that means we have a -2 here, so this has to be a +2. So it has to be iron 2. We're going to need that when we write it as an ion here in just a moment. How about potassium hydroxide? Well, that's pretty straight up. Potassium is right here. It's a +1. Hydroxide is, oh, I lost it. Where is it? Right there. And it's a -1. So those two just go together 1 to 1. Okay, so this is 1 plus, and this one is 1 minus. Okay. All right, there we go. Now we switch the cations. So now over on this side, we're going to end up with, oh, by the way, we first, well, let's go ahead and switch the cations first. Yeah, I was going to check solubility. Let's do this first. So we're going to take the iron, which is a cation. It's a metal. It's a positive charge, and we're going to put it with this over here. Okay. Now we see that iron is a 2 plus and the hydroxide is a 1 minus. So that means we need 2 hydroxides to balance with the iron. The iron's going to give off 2 electrons. Each hydroxide can catch 1, so you need 2 hydroxides. So you put the parentheses and put a 2 right there. And go ahead and write the charge up here. So it's 2 plus, and this one is 1 minus, and then you multiply that by 2. So you have a balanced charge there. All right, next is the other one. It's potassium nitrate. So it's K. And we can go ahead and put the charge up right now. And then it's NO3. Now, just because there's a 2 there doesn't mean you put a 2 over here. You want to see what it takes to get this to balance. So it's NO3. Okay, and we just looked at it. So nitrate is a -1 minus, and potassium's a 1 plus. So we don't need any subscript out there, which means I really didn't need to put the parentheses around it. So it's a 1 minus. Okay, so we now know that the charges are all balanced. So now what we want to do is check solubility. So we can go ahead and put our phases after each of these compounds, whether they're aqueous or solid. So let's go ahead and get the solubility rules out again. So iron nitrate, well, nitrate is up here in the top row. Those are the guys that dissolve with anything. So it definitely dissolves, so that's aqueous. Potassium is also in that top row. It dissolves with anything, so that's aqueous. So that means we have a reaction here. We may have a reaction. If either of those did not dissolve, you wouldn't have a reaction because you wouldn't have been able to swap the cations. Okay, now we come over to this side, and we have iron hydroxide. Let's look where I'm pointing, iron hydroxide. So we look over here, and we see that hydroxide is in the insoluble column over here, and iron is not one of the exceptions. So that means iron hydroxide is insoluble. That means it's going to form a solid. So I'm going to put an S there. And finally, we have potassium nitrate. I think you know by now, you look at your rules, both of those are soluble with anything, so that's aqueous. That means potassium nitrate is never going to really form a compound. They're just going to float around as potassium ions and as nitrate ions. Okay? So it's kind of the same situation we had in the last problem where you have a single precipitate there. Okay, so now you're ready. This was your complete molecular equation. In other words, these look like molecules, even though they're not molecules. They're ionic compounds, do not form molecules. If you're still curious about that, don't worry about it right now. We'll talk more about that concept later. Okay, so complete molecular equation. That's the first of the 3. The second of the 3 is the complete ionic equation. Okay, and that's the long one. That's when we're going to break everything out. So here we go. Oh, we need to balance first. Didn't balance. So what do we have to do to get this thing to balance? All right, so I didn't leave myself a lot of space to put a number there, so let me do this. Okay, so let me do what I did last time. Let me rewrite it down below. So before I do that, let me write Fe. I'm not going to write all the aqueous in that, again, because I want to make it as clean as possible so you can see what I'm doing. KOH is there. There's your arrow. So notice what we did. We used charges to determine the subscripts of these things here, okay? We used charges for that, but now we're going to balance the equation the way we've been doing for a month and a half now to get the coefficients that go in front. So understand how we got these as opposed to how we get what eventually going to go in front. Okay, let me raise this up a little bit here. All right, so we got that, and now we got potassium nitrate. And I don't need the parenthesis there because there's no subscript on the outside. Okay, so let's balance this. So what do we have? We have iron. And watch, I'm going to do my little trick again here. This is a hydroxide, that's a hydroxide. You can treat it like it's a single element. It's not, the O and the H are not going to break apart. So I'm going to call that an element. It just simplifies my numbers. I have a nitrate. This is not going to break apart. This N and this O are not going to break apart. But if you're comfortable doing it, you can say this is 3 O's and 1 N. And you can say this is 6 O's and 2 N's. If you want to do it that way, that's perfectly good. Or you use the box method. It always works either way. Okay. And finally, what else do I have? Potassium. And I'm ready to go. So I got iron. I got 1 on each side. Hydroxides. I got 2 on this side. And I've got 1 on this side. Nitrates, I've got 2 on this side, 2 of all of that, and 1 over here because there's no subscript outside of the NO. And potassium, there's 1 here and there's 1 there. Okay, so potassium and iron are in balance. So let's start with hydroxide. So we have 2 on this side, so we're going to put 2 on this side, put a 2 up there. So that makes that a 2. All right, and so two hydroxides and 2 hydroxides. Now I have 2 potassiums and I only have 1 on this side. So I also changed potassium. I got to change that number too. So I've got to put a 2 over here. So now I have my potassiums are back in balance again. And now I have 2 nitrates here. Again, remember, this is just an NO3 with a 1 behind it like that. So it's 2 nitrates and I have 2 nitrates here. So that's in balance already. So now I change that. And iron, I never touched that. So that's good. So it's 1, 2, 1, 2, it looks like is what we have. Let me just count. So I want to count and be sure. So I got Fe and Fe. I got OH. I got 2 OHs and I got 2 OHs right there. I got 2 nitrates there and I've got 2 nitrates there. And I've got 2 potassium and 2 potassium. So everything's good. So it is. It's 1, 2, 1, and 2 down here. Okay. All right. So what does that mean? Be sure you understand what that means. It means on this side, I'm going to write 2 potassiums, 2 K plus, and I'm going to write 2 OH minus. And over here, I'm going to write 2 K plus and 2 NO3 minus. So let's go down here. Now I'm ready to write complete ionic equation. This is the long one, the middle one. Sorry, let me get back on screen. Just yell at me, yell at your computer if I'm off screen like that. Equation, okay? So here we go. All right, so we have 1 Fe, and I'm going to use the charges up here, but I'm going to go with this. So I have 1 Fe, so it's going to be Fe 2 plus, because we decided that was an iron 2, not an iron 3. All right, plus, and I'm going to have 2 nitrates. These nitrates are going to break apart. They're not going to stick together. So it's 2 NO3. And those are minus ones, 1 minuses. Plus, I come up here, I'm going to have 2 potassiums, so that's 2K plus. I'm going to have 2 hydroxides, so that's going to be plus 2OH minus. Now I'm ready to go over to the product side. I'm going to have 1 Fe, that's still a 2 plus. Well, I take that back. We said that's going to be our solid, our precipitate. So it is simply, and we didn't have to put any coefficient in front of it except a 1, so it's FeOH2, and that's a solid. We said that hydroxides, again, hydroxides are insoluble, and iron's not an exception to that, so that's our solid. And now we're going to finish it off. We have 2 potassiums, so that's 2K1 plus. Plus, we have 2 NO3s, so that's 2NO3, and that's a minus. That's a 1 minus. Okay, each NO3 is a 1 minus, okay? All right, there it is. So now we write our net ionic equation. All right, and here we go. So, what do we have that's the same on both sides? Well, Fe is not the same. There it's Fe, it's an ion right there, but it's part of our compound over there that was insoluble. So that's not. So I'm going to circle those because we're going to keep those. I have 2 NO3, and I have 2 NO3 over here, so that's a spectator. Doesn't change, doesn't affect the reaction. Okay, and then I have 2K here and 2K here. Spectator doesn't affect the reaction, just sits there and watches. And finally, we have the 2OH, but that becomes part of the compound here, so I'm going to circle that. So the net ionic equation for this is Fe 2 plus 2OH minus, so you have 2 of the negatives and 2 plus 2, so that balances, and that comes over here and forms the compound of FeOH2, and that is your net ionic equation for that. Okay, here's a limiting reactant problem. We need, a lot of us need to practice these. So we're going to go ahead and do one here, very similar to the one you had on the test. Again, the point you got to drive home in your mind is these represent molecules or atoms or moles. They do not represent grams. You cannot put grams into a limiting reactant. Chemical equations don't understand grams. It's a totally foreign number to them. They don't measure things in terms of how much they weigh, which is what grams is. So you already have an already balanced equation. So first thing we're going to do is we're going to convert this is what we are given to work with, and we're going to convert that into moles. So we start off with this. I'll go ahead and set up the other equation right now. So we have 28.7 grams of oxygen. Okay, and we'll go ahead and run those numbers. Okay, so I do my calculation there, and what I have to work with then in moles, which is the only thing chemical equations understand, is this and this. So this is how many moles of C3H6 I have to work with. This is how many moles of O2 I have to work with. So now we're going to set up our two equations. You have to run the reaction twice. First time we're going to run it is with all C3H6. We're going to use every bit of it that we were given. The second time we're going to run the reaction again with all O2. We're going to use every bit of that. That's my O2. Okay. All right, so I'm going to just draw my boxes. Do that if you like. Don't do it if you don't like, but you can just write the numbers down. Okay, so what we know we have a C3H6. We're going to put in the all C3H6. We're going to use all of it. It's 2.1 moles. And in the all oxygen, we're going to put the 0.9 that we have there, moles. We're going to circle those because we know we have that much. Now we have a very odd relationship here. It's not a nice simple 3-to-1, 2-to-1 like you've been used to seeing. So how do you get that? Well, you take this number. This number is going to be 9/2. If you like to convert that to a decimal, that's 4.5 or 4.5. You can do that if that's something you're capable of doing. But what if it was some really odd number you couldn't just quickly convert? You multiply this by 9, but then you have to divide by 2. So that's what I'm going to do. So I'm going to do that right here. I'm going to say 2.1 times 9 divided by 2. So that's 4.5, 4.5. And it gives me 9.45. I'm going to end up with 9.45. Should really put 9.5. I'm going to go with the 4.5. Okay, now this one going in the opposite direction, you need 9 moles of this for every 2 moles of this. So you need a lot more of this than you do of this. So that means it's going to be a division. It's going to be in the opposite direction. So I'm going to take my 0.9 there times 2 divided by 9, and that gives me 0.2. And that's pretty obvious, isn't it? If this is 9 and this is 0.9 and this is 2, then this has got to be 0.2, right? So that makes sense logically, right? Good. Now we're going to go around and see which ones we have. We know we have this. We know we have this. Okay, now the question is, do we have at least 9.45 moles of O2? Heck no, we only have 0.9. It's a crazy problem. So the answer is no, we don't have that. How about this? In order to run this reaction, I should have pointed out what that was. In order to run this reaction to burn all, combust to burn all 2.1 moles of this, we need 9.45 moles. Do we have that much? And we just said no. Now to combust all of the O2 that we have, that's 0.9 moles of O2, we need 0.2 moles of C3H6. Do we have at least that much? Yeah, we have a lot more than that. We have 2.1. So this is a yes. So this is the no column. So that means our limiting reactant is oxygen. An excess reactant is the C. It's got to be the other one. Okay, how many moles of excess reactant remains after the reaction? So this is the limiting. This is the excess. We were given 2.1. We only had to use, because this is the reaction that's actually going to work because it has the 2 yeses in the column. So this is the reaction that will actually work. So we were given 2.1. We only used 0.02. So it's 2.1 minus 0.2, which equals 1.9 moles of the excess is left over. Okay, not too hard. All right, now what's the next question going to be? And it's on the next page. How many moles of CO2 are produced? So what we want to know is moles of CO2. So this is the chemical reactions world. It's all in moles. Everything we're talking about is in moles. So we have 6 moles of CO2 for every 9 moles of O2. That's an ugly relationship. Or we have 6 moles of CO2 for every 2 moles of C3H6. So we have 3 times as much CO2 as C3H6. So if this is 0.2, you can kind of do this one in your head. 3 times that is 0.6. So the answer to that question on the next page is you have 0.6 moles CO2 produced. How many grams of water are produced? Okay, so we come over here. We first have to convert to moles. Okay, so put a box there. So again, we're still in chemical reaction world here. We're dealing with moles. So you see 6 here, 6 here. It's got to be the same number, so it's also 0.6. But now we got to come out into our world. We need a number in grams. It's asking us for grams of water, because we want to know how much we get to drink, because we get to drink the water, so I want to know how many grams. I don't want to know how many moles. So what's the molar mass? 1 mole H2O equals 18.02 grams. Again, it's 16 plus 1.01 plus 1.01. You just have to add up the masses of each of the elements. And that's grams of H2O. So I got 0.6 moles, and I have that molar mass, so I'm going to take this off the screen and go over here. So I have 0.6 moles of H2O, and I'm trying to get to grams, so 18.02 grams of H2O. Cancel, cancel, and you got 0.6 times 18.02, so that is going to give us that's going to give us 10.8. So many grams of water we'll get. Not very much. Okay, there's your answer. Okay, all right, now I'm having you always going to be practicing these names. So get out your 60 ion sheet that we were using in the earlier part of the set. And let's go ahead and name these. Okay, so CaOH. So that's a metal, and that's a cation and an anion. Okay, so that's simply calcium. The cation keeps its original name, and the anion is, well, this is a hydroxide. So, all right. Okay, these are two nonmetals. That means it's a covalent bond. Okay, so this is going to be phosphorus. This is the one where you use the prefixes mono, di, tri, tetra. Okay. But you don't use mono in the front of the first of the two, so it's just phosphorus. Trihydride. Okay, next one is lithium and nitrogen. So again, that's a metal, non-metal. So it's just lithium. Don't use any prefixes here. Lithium nitride. It's not nitrate or nitrite. It's not a T, it's a D. Okay, I'm going to underline the D to emphasize that. Okay, nitrite is NO2, NO3, excuse me, it's NO2 minus. And nitrate is NO3 minus. Okay, next one is iron sulfate. That should be a lowercase or a subscript 4. Okay, so it's iron and sulfate. Now we got iron has more than one charge, so you have to identify which is it, iron 2 or iron 3. So what we do is we come over and we look at sulfate. That doesn't have a variable charge. Sulfate is a -2, a 2 minus. And this says that there's 3 of them. That means the sulfate, let's go ahead and write it over here. We got Fe, and we're trying to decide what this is. The sulfate is a 2 minus, and there's 3 of them. So that's going to make it a 6 minus. So that means the iron has to be a 6 plus. And it says that there's 2 of them. So what do you multiply 2 times what number gives you 6? That would be 3. So it has to be iron 3. So over here we're going to write iron 3 sulfate. Sure, I'm not off screen here. Okay, iron 3 sulfate is what that compound. So you had to play around with the charges a little, figure out the charge. You're going to have to do that when it's a transition metal, because many of them have different charges. Okay. Okay, the next one is a metal and a non-metal, carbon, aluminum and carbon. So it follows the same rules for ionic bonds. It's aluminum and car, and then you end it with an IDE. So it's carbide, aluminum carbide. Okay, now we're going to go in the other direction. We have lead 2 and oxide. So lead 2, let's go ahead and do the charges. Lead can be either a 2+ or a 4+, but it says it's a 2+. And oxygen is always a 2-, pretty much always. There is a couple of rare exceptions. So it's simply going to be PbO. Those two match up 2 to 2. All right, next is diphosphorus. So that means we're going to have a P2 pentoxide, and that means it's going to be an O5, pent is 5. Okay, silver sulfate. Now if you go to your charges, silver is a transition metal. But if you look at your charges, Ag, it only has one charge state, a +1. So you don't have to write a Roman numeral for silver. So it's going to be Ag, so it's a +1, and sulfur is a 2-. So sulfur wants to take in 2 electrons, but silver only wants to give up 1. So you're going to need 2 silvers, each throwing 1 electron off, to fill up the sulfide. So it's going to be Ag2S. Calcium phosphide, so calcium is going to be a Ca. And phosphorus, there's phosphorus, that's the phosphide. So what you got to do is look at the charges. Calcium has a 2+, phosphorus has a 3-. So in order to make them balanced, you're going to need 2 phosphoruses. 2 times 3- gives you -6, and 3 calciums. 3 times +2 gives you +6, so +6, -6. But remember the little trick, you can take the 3, forget about the minus sign, bring it over here, and take the 2, forget the plus sign, put it over there. And so what you have is Ca3P2. That's the answer there. Finally, potassium oxide. So potassium is a +1, a 1+. Oxygen is a 2-. So you can do the same thing. You can take the charge and bring it over and make it the subscript of potassium. Take the charge, bring it over, make it the subscript of oxygen. So you have K2, because each one has a +1 charge. That gives you 2. And then oxygen has a -2 charge all by itself, just one of them. So there you go. And that's your final answer there. Okay, so I hope you got all these done. If you didn't totally understand everything here, it's a challenging subject, Net Ionic Equations, and we'll practice it a lot. And hopefully we get our limiting reactant problems, we improve on those a bit. And that's it. We'll see you in class.